So here comes chapter 11. So in chapter 11, it's called the chi-square distribution. So hopefully you've read the first, about the first half of the first page of the lecture before we get to practice problem number 1. The chi-square distribution is a type of distribution that we haven't spoken of yet. We've seen, right, the normal distribution is the big one, but we saw exponential distribution, uniform distribution, that sort of thing. So the chi-square, C-H-I is a Greek letter, chi. Totally different look. It's got a similarity to the normal distribution. And when we pull it up in the StatCrunch calculator, at one point, you'll get to see it. Anyway, the point is, and what this chapter is all about, we are able to investigate different types of questions and perform a hypothesis test on them. So this is our final chapter on hypothesis testing. We do also have chapter 12, but that's going to be a whole different concept. So what's going on here with the chi-square distribution hypothesis tests? So there are two types. There's the goodness of fit, which we're going to see in practice problems 1 and 2. And then there's also the test of independence, which we see in number 3. So this lecture is only 2 pages. Really, really nice. Well, hey, let's jump into practice problem number 1. And in the reading, really all that there is kind of just giving you a basic idea of what the goodness of fit is. Does observed data fit a particular distribution? And there's a new formula for the test statistic. And so we're going to see that obviously play out in this problem. So let me read practice problem number 1. An employer of a large company wants to know if his employees call in sick more frequently on certain days of the week. He wants to believe employees are sick equally throughout the week. So over 60 weeks, the employer notes the day that most employees call in sick. And we get this table of the work week, Monday through Friday, and how many times was each day the most popular day, the day that most employees would call in sick for that given week. So Monday was the most popular day to be sick 14 times, right? Tuesday, the most popular day to be sick 10 times, and so on. And then eventually see Friday, the most popular day to be sick 16 times. Kind of dips there in the middle of the week, so well, maybe not too surprising. People call in sick more often on Mondays and Fridays than on Wednesday, or let's say. But the employer wants to believe, he's going to assume that people are sick equally through the week, and then at the end there it says, conduct a hypothesis test to decide if the number of days that most employees call in sick occur with equal frequency, and use alpha equals 0.05. Okay, so we're gonna start with it's our same steps for the hypothesis test, right? I haven't gone through and written them out, but right, step 1, your null and alternative hypotheses. Step 2 is your test statistic, and that's where the formulas vary. Step 3 is your p-value. Step 4 is to compare your p-value to your alpha, your significance level. And finally, step 5 is to decide, either reject or fail to reject the null hypothesis. Okay, so let's get into step 1. Of course, we call it H0. And what's the assumption? Well, it said it right there in the problem about the second sentence. He wants to believe employees are sick equally. So I said sick days occur with equal frequency. Now you notice something about the chi-square. There's not an equation that we write here. There's no mu or p or equals 0 or anything like that. It has to be a sentence, just the way that these problems are going to work. So there's our assumption. Sick days occur equally, or you might say with equal frequency. When it comes to these sentences, you're going to do whatever seems natural to you, being sure to be clear what you mean. You might not phrase it exactly the way that I did. You might say sick days occur equally throughout the work week. or sick days occur equally from Monday to Friday, something like that. Any of that works. So what's the alternative? Now, the alternative hypothesis, very simple. Once you have the null hypothesis, we're just going to put a negation in there. So we're going to say that they do not occur with equal frequency. So it's just always simply the opposite of the null. Sick days do not occur with equal frequency. Or just somehow negate whatever it is your alternative works out as the way you write it. Okay, so null and alternative hypotheses definitely have a different feel here, as will the test statistic coming up next. So we saw this formula. Okay, now I abbreviated it. This right here, that is not an X, and even the way I've written it isn't quite right. This is the Greek letter chi. It kind of swooshes through and then crosses like that. And that's a capital chi. All right, it's equal to, we've got our summation symbol, observed minus expected, quantity squared, divided by the expected. All right, what does that mean? Here's the way we're going to approach step 2. We're going to create a table. Okay, this way really keeps your work organized really well, keeps it nice and tight, so you don't have little calculations going on all over the place. I'm going to put Monday, Tuesday, Wednesday, Thursday, Friday as columns here at the top, and my rows are going to be the observed. Then we're going to have the expected. We'll fill that in a moment. Once we have the value for the observed and expected in each column, we're going to calculate observed minus expected squared divided by the expected. And I've got my calculator ready right here. Okay, so I'll give you a moment to draw that table for yourself. Maybe hit pause. So I'm going to go on. Where did I get these numbers? Well, obviously those are the numbers that were given to us in that table. So these are the numbers that the employer observed as he surveyed those 60 weeks, right? Monday was the most popular day to be sick 14 times, and so on. So that's what he observed. That's the data that he collected. Okay. What would he expect? Okay, this goes back to the null hypothesis. He expected that sick days occur with equal frequency. So how should we fill these in if he expects they occur with equal frequency? Well, I'll give you one hint. They should all be the same number because they should all occur equally. But what number is that? Now, this would be a lot better if we were in class together, because then I could what number do you guys think we should put in right there? Here's what we should put. I'll put it over here to the side. He did this for 60 weeks, right? And there are 5 categories. So what's 60 divided by 5? 12. If he looked at 60 weeks and they occur with equal frequency, then they should all be 12. Because that adds up to 60 and they're all the same, right? Okay. So some of them were a little bit low, some were a little high. Thursday was spot on, but okay. Without the details of the explanation, here's what we're going to calculate. There's kind of a similarity to like variance, right? Like you subtract and you divide. That variance had that sort of the variance formula way back in chapter 2 had that sort of a feel to it. And there's really the same idea. When we take the difference, we're seeing how far away from what was expected are we. Okay. So let's do that here. We got 14 minus 12, of course, is 2. Then we square. The squaring will always turn it into a positive. Because we want the error to be positive, just like in variance. And then dividing by the expected, again, kind of gives us that ratio, like how far away were we. Okay, because how far you are depends on the value there as well. Right. So here, I think I'm explaining too much. Let's just go for it. So 14 minus 12 is 2, squared is 4, and then 4 divided by the original 12 right there. And I just gave the fraction version for this one 1/3. Okay, let's go on to the next one. And let me show you what I'm doing here. So I got 10 minus 12 squared divided by the expected again, 12. That's 1/3 again. Okay. Moving on. 8 minus 12 squared divided by 12. That is 4/3. You might use decimals here, Hey, what's this one going to be for Thursday? 0. Because it was perfect, so there's no error. And then finally for Friday, 16 minus 12 squared divided by 12. Again, at 4/3, 1.333. Okay, so we have calculated observed minus expected squared over expected for each of our 5 days. What are we going to do then? We still need to do the sum, so we're going to add all of those up, and at this point we want to convert it to a decimal. So when I add those together, hey, they're all over 3, so that's 2, 6, 8, 2, 6, 10. 10 over 3. 3.33. However you do it, decimals, fractions, 3.33. Okay, that right there, that's our test statistic. Chi-square equals 3.33. And you kind of, what a bizarre way to name your test statistic, right? Chi, well, all right. We got a new Greek letter. The square, of course, comes from the fact that we're squaring right there. So it's just part of the name, chi-square. All right. Hey, we got it. Moving along to step number 3, the p-value. Let's discuss this because really going to feel very similar to previous p-values, but there's nuanced differences. So we think the p-value equals the probability that chi-square something 3.33, and here we need to choose carefully. Do we want a greater than or a less than? Normally we'd go back to our null hypothesis, but it was just a sentence here. Let me tell you, for chi-square, this is really nice. It's always greater than. Always. It's just the way the distribution works. And we'll see that in the graph of chi-square. Okay. Always. Every problem. It's always a greater than. So what do we do? All right. Go to your StatCrunch chi-square calculator if you don't have StatCrunch pulled up yet. Pause this video, get over there, log in, locate the chi-square calculator. Make sure you've got a greater than. Type in 3.33. We also have a degrees of freedom for chi-square, so we probably shouldn't move on until we talk about that. Very similar to our original degrees of freedom. You see it there in the lecture. It's the number of categories minus 1. Well, let me go back to the table. How many categories did we have? And, well, there were 5. Monday, Tuesday, Wednesday, Thursday, Friday. 5 categories. So our degrees of freedom here is 1 less than that, 4. Okay. Hopefully you have your StatCrunch calculator pulled up. Your chi-square calculator. 4 degrees of freedom greater than 3.33, and you should get 0.5042. I'm pretty sure I rounded that to 4 places. And now you can see the look of the chi-square. I'm not going to show you my screen or anything like that. But the chi-square, right, so it starts at 0, and then it's got like a bell curve kind of a look to it, but it shoots up really high, and then it sort of drops and it trails off this way, right? So it goes infinitely far in the positive direction, but it never goes negative. So it just stops right there. So what we're doing when we find this p-value, depending on your degrees of freedom, 3.33. I have no idea where it really is for our graph, but I'm just gonna guess right there. So 3.33, and then it's gonna think of that area. It's all that area behind. So it's always, actually, if it's a greater than, then it's this area, isn't it? All this area up this way. Oh. Okay. Anyway, so it's got kind of a bell curve sort of a look to it, but it gets elongated. So because we're only dealing with positives, that's kind of the reason for the greater. Okay, moving on. Step number 4. We're going to compare the p-value that we got with the alpha. So they said use alpha equals 0.05. Well, which one is it? Well, of course, the p-value is bigger here. Also, another thing to note, when it comes to chi-square, we're always using alpha here. Sometimes in the previous chapters, we've had to use alpha over 2 because we had to think of, a little bit above, a little bit below. That won't ever happen with chi-square because it's always one directional, one tail. So that's always simply alpha. We never divide that in half with chi-square. So really nice. All right, so our p-value is bigger. What does that mean? Do we reject or do we fail to reject? We fail to reject the null hypothesis if our p-value is bigger, and it's way bigger. I mean, it's 10 times. If you think here, that the alpha would have been way back down this way. And so if we think of the alpha creating the shaded region, did the p-value make it into that shaded region? Well, definitely not. We definitely did not get inside that shaded region. So we failed to reject the null hypothesis. And just to give you an interpretation in a sentence, in case you need that, there is not enough evidence that sick days do not occur with equal frequency. That's surprising. You would think that looking at that table, oh wow, Fridays are really heavy, Mondays are really heavy. Turns out we don't have enough evidence that sick days do not occur with equal frequency. We have to just err on the side of the null hypothesis, that everyone's being honest. But you know what? If the employer, if the guy who runs the company is still suspicious about his employees calling out sick more so on Mondays and Fridays, what might he do if he, even after testing like this, he still isn't really sure? I mean, he's got some evidence, right? Well, he could just collect more data. So instead of 60 weeks, 60 weeks is more than a year, but he might collect data for maybe another round of 60 weeks, and then maybe more data will end up giving him more evidence. Maybe not. So not all is lost if he's still suspicious. Okay, we're going to stop this video here. We will do practice problem number 2 in the next one.